All right, so we're going to talk about reaction mechanisms for lesson number 12. One of the things we talk about in this lesson is reaction progress diagrams, where we look at the progress of a reaction and the energy associated with this. So we have the beginning of the reaction going to the end. So the beginning of the reaction is reactants, the end is products. And in the middle, we have transition state. Transition state is high energy. Now, from a reaction diagram, we can figure out some things. First, this right here, this is my activation energy, the difference between transition state and reactants. This, the difference in energy between products and reactants, this is my delta H. Okay, so let's go ahead and let's calculate these two values. So delta H is always going to be the energy of my products minus reactants. We learned this already in thermochemistry or thermodynamics. So my products, it has 0 and 50, and there's a dashed line in between, so that's at 25 kilojoules per mole. And my reactants are at 125. So the difference between these two will be negative 100 kilojoules per mole. Notice that it's negative. Why? I'm going from high energy to low energy. That energy is leaving the system. This is exothermic. All right, our EA is going to be transition state minus reactants. All right, so my transition state, that's at 150. My reactants are at 125. That's going to get me positive 25 kilojoules per mole. Okay? The energy of activation is always positive. I can't have a negative energy of activation. Because remember what that is. That's the energy barrier between reactants and products. All right, let's go on and let's go look at part B. In part B, we're asked about the reverse reaction. Okay, so the thing with this is, in order to understand the reverse reaction, we have to go ahead and we need to flip this. What was products is now reactants. What's reactants is now products. So what we're going to get is right? So this is now at 25, this is now at 150, and this is at 125. Basically, I turn my products into reactants, my reactants into products. And now I can go ahead and I can label my delta H is this difference, and my EA, my energy of activation, is this difference. Okay? It's not just this bump, because activation energy is from reactants to transition state. It's the energy to get over that. Okay, so let's do this. My delta H will now be 125 minus 25. So that's going to be positive 100 kilojoules per mole. Okay. Notice how this reaction is negative. It's exothermic. So that means this one is endothermic. Okay. And we can figure out EA. This is going to be transition state minus reactants. So 150 minus 25. So that's going to be 125 kilojoules per mole. All right, so we did it one direction and then we reversed it and we could figure those out. If we look at these on the screen, what we can see is that my delta H between the two, it just flips, right? Negative 100 to 100. That's because that's what we learned in thermochemistry, thermodynamics, right? Flipping a reaction flips its delta H. But notice the EA, right? It doesn't flip, right? It's more complex because you have to take into account the difference in this hump. All right, but EA is always positive. Okay, let's move on to video problem 12B. This one involves looking at a reaction mechanism. So in this case, we have 2A going to B plus C, and then we have B plus D going to form E. We're told that this is slow and this is fast. Okay? So we're told that these two reactions come together, and that's a reaction mechanism. So if I want to know the overall reaction, what I do is I just add these up. So I have 2A plus B plus D goes to form B plus C plus E. Notice the B I have as a reactant and as a product, so it goes away. That's 2A plus D goes to C plus E. All right? We have a special name for something that gets formed in one and then gets removed in the next. This is called an intermediate. Right? B is an intermediate. Okay, what are the rate laws for each elementary reaction? Well, because they're elementary reaction, remember what is an elementary reaction? It occurs exactly as it is specified, right? So 2 A's actually come together. So that means this one is rate equals K times A squared. And then this second one is rate equals K times B times D. Now, these aren't necessarily the same K, so we have to signify. We'll call this one K1, this one K2. D. D asks what the overall rate law is. Well, because the slow reaction is first, that means that this is the one that defines it. Okay? So my overall rate law is only due to this one. So rate equals K1A squared. Okay? If the slow one was the second one, it would be more complex. We don't deal with those here. All right, and then finally, what's the rate limiting step? Rate limiting step's always the slowest, right? The rate limiting step in you getting your degree isn't actually going up and shaking the president's hand and getting the degree. It's all the work you have to do over the years, right? So this is my slow step. That means it's the rate limiting step. All right. Okay, so that's it for mechanisms. This is the end of the second section on kinetics. So make sure you come to office hours, SI, etc., and ask those questions. All right, talk to you later. Oh, let me just put this up just so that if it's not clear here, you can see it on the screen. All right, talk to you later.